Hello everybody, my name is Bogdan Nicolae, and today I'm going to try to combine two important concepts, the second law of thermodynamics and the polar functions. So let's get started. Firstly, I'm going to try to give a raw explanation of entropy. Imagine having two glasses, glass A and glass B, both containing three liquids, but with a slightly difference. In glass A, the liquids are in an ordered form, compared to glass B, where they're just spread around the glass, chaotical, mixed. At the first glance, you would rather think that the glass A is the natural state, but it's wrong. The possibilities of having a disordered state is way bigger because of the various methods of mixing them. Whereas in the state A, we have only one possibility. Also, the universe tends to a greater amount of disorder, a law dictated by entropy. A fallen egg will splatter, a fallen glass will break, because it's the more natural way, the way towards disorder. That was a simple explanation. On the following, I'm going to try to explain the polar function and then combine them into a new framework. So now I'm going to try to explain the polar function. I think the best methodology of explaining it will be just by making an example. So we have r of theta equals theta. For simplicity, I'm just going to limit theta between 0 and 360, 2 pi in the trigonometrical form. The classical functions, you have an x and an I. You're just going to plot them with coordinates. But now we have the radius and also the angle. The angle dictates our length of radius between 0 and the point where it should be, so this distance. I'm just going to plot this. So for 90 degrees, pi over 2 will be here. For pi, the double, 2 pi over 3, of course, and 2 pi around here. So all this function will just look like a spiral. When we actually the spiral is just gonna go forever and forever, but our limit is just gonna simplify it. Now I'm gonna take another function, this time with a, which is pi over a, where a is a natural number. For a equal 1, we're just gonna have a circle with a radius of pi. The next one's gonna be pi over 2, and the list will just go on and on. If we put the same parameter in the first function, our spirals will just get smaller. I'm just gonna put it there for, I think it's way easier. Spirals will just become smaller and smaller, but at the same time also the circles. But the real question is, what happens when you have 10 A's, 20 or 50? Okay, so here I plotted the values for the two functions, R1 and R2, for values of A between 1 and 25. Actually, this isn't the complete function, it's a zoomed in version just to see the critical information. As we see, the intersections between the functions are quite chaotical, but also, as we look at this part of the axis, we see that not every intersections are satisfied between the functions because of the different ratios of for example, 2 pi over a and pi over a and pi over a. But I found a way to determine the intersections on every axis, on pi over 2, pi, 3 pi over 2, and 2 pi. And I'm just gonna write them down. Okay, so here I have my conditions for the point P, which will satisfy the intersections between, as I say, R1, R2 on all the 4 axes. Let's start with P1. I just multiplied A by 2 because I'm working at a 90-degree angle. The second one, it's way more easier. I just let it natural, as we say, because pi over A satisfies pi over A. The third one, I took this relationship, this fraction 3 over 2, inverted it, and put it above P in order to get my 3 up there. The A is just going to follow the symmetry. The fourth one, because we're working on 2 pi, I just multiplied my R2 with 2. Here I have my function system again. Right now I will try to satisfy this axis with my last function, pi over 25, theta over 25. So we're just gonna equalize it. So here we have like 2 pi over 25 equals with 2 pi over 25. So this condition is correct. I won't do the other ones because I try to keep the video as short as possible, but if you want you can like test them. Right now we're gonna see what's happening if we're plotting this condition. Alright, so as we've seen, the last R1 function got satisfied by the intersection, as we say. When we compare these two systems, we see something very interesting. We can see that the left one has a greater amount of entropy than the right one, and bam, as a statement we can say that my conditions favorize the entropy. So when I satisfy them, the entropy is just gonna grow. The system is gonna become more natural. Right now I'm just gonna try to formalize everything. Okay, so I just took the function, duplicated it, and substituted it with b. B is a natural number as a. When b equals a, as seen in this system, we have a low entropy out of equilibrium state. The equilibrium states are part of the thermodynamic states, are a characteristic actually. I won't describe them right now because I don't have the necessary time, but look at these two systems. When we compare them, this is kind of a little bit more sketchy seen as in the symmetrical perspective compared to this one, and I personally define this like in a bigger equilibrium. Also because of the high entropy, when B equals 0.5a, we have as I said a high entropy equilibrium state. So in this short video, I've combined entropy with polar functions. When a is 0, by dividing a number with 0 we get a singularity. Black holes can be defined as a singularity or the Big Bang theory. But the black holes are also objects and entities with a huge amount of entropy. So when a approaches 0, the entropy will also get huge. But also when a approaches infinity, our functions will get smaller and smaller, closer and closer to 0. All the intersections will also get closer and closer to 0, and this means that the entropy will also reach its maximum. So we can just schedule it as a cycle. We start with 0, the entropy gets smaller again, then we end with 0. My attempt to combine two important concepts was really like a journey for me to the realm of science. I hope you enjoyed it too. Thank you for your attention. Science for the week.